Thank you everybody. Today we're going to have Dr. Jianming Wen from the Kennesaw State University to give a talk about the quantum mechanics. The reason I'm saying that because it's so complicated for me actually, but I know it belongs to the quantum mechanics. I know Dr. Wen for a while. Right now he just got promoted to the associate professor, right? Congratulations. And another good news from him that I think few months earlier, just won the NSF grant from NSF, lead a big team to work on the quantum mechanics. And right now he have totally from a lot of support from DOE and NSF. How much? 1 million? More than that, right? Congratulations, really amazing work. And by the way, so Dr. Wen graduated from the University of Maryland and worked in the Yale University as a research scientist, right, for 4 years, and then joined the KSU in 2017. And we know each other from 2018, just after I joined the GSU here. Okay, so let's give the time to Dr. Wen. Thank you so much.
Yeah, thank you for the introduction. It's really my pleasure, to be here. This is my second time to give a colloquium here. So the previous one that's back before the COVID-19, and that topic has nothing to do with quantum. Okay, so that's purely just classical. We look at non-Hermitian physics, if anyone recall. So we're talking about the parity and the symmetry. So this time has nothing to do with the symmetry stuff. We try to jump into the jungle of quantum information science. We want to ever look at how photons and the neutral atoms they gonna play the role that allow us to build up quantum computer or eventually the quantum network. So welcome it's really my pleasure to welcome you to this talk on the fascinating world of quantum information. So today we will dive into the reality of single photons and the neutral atoms. Exploring the cutting-edge field at the intersection of quantum mechanics and information science. So we will jump into a journey to harness the properties of single photons and neutral atoms and pushing the boundaries of what's possible. So in the next few minutes, we will uncover the fundamental principles behind quantum information, from superposition to entanglement, and see how these principles drive our pursuit of quantum supremacy. And we'll also look at our latest breakthrough, including narrowband biphoton generation and reliable triphoton generation. So as we venture into this exciting frontier, let's embrace the awe and the wonder of quantum mechanics and envision the profound impact of the impact that it may have on our technological landscape. So during the talk, if you have any questions, please feel free to stop me ask. All right. So a classical base serves as the smallest units of data in traditional information processing and computing, symbolized as either 0 or 1. It's like a light bulb, whether it's on or off, a straightforward true or false statement. So as an example, consider this digit 5. It can be represented by 3 classical bits in this binary format. So then now let's introduce a quantum bit or qubits. So it's a remarkable quantum concept that exists in the superposition of 1 and 0 simultaneously. So imagine we have 3 such qubits, and each in this superposition state. Then immediately we can represent, or we have whopping to the power of 3 potential states, which translate values from 0 up to 7 in this binary format. And if we scale up to 300 such qubits, then we will have astonishing to the power of 300 possible states. And that's the amount of information. If you use a classical base, turns out there is no such amount of atom in the entire universe allow you to impress the same amount of information. And that's the incredible power of quantum computing. Essentially, the magic of superposition leverage the information processing in ways that the classical base simply cannot comprehend. And this is the promise and the potential of quantum computing, a territory where where the seemingly impossible becomes reality, right? So if you look at this, if 2 goes to the power 300, that's already way beyond the total atom in the whole universe. So that's why quantum computing is a big driving force in the current research. So this is certainly pretty exciting. So the superposition allows us to do pretty cool stuff. So it can allow us to process to the power of n for all n input qubits all at once. It's like taking a massive puzzle with 10 of pieces all at the same time. But here's where it gets tricky. When we try to measure this superposition, it doesn't give us a straightforward answer. Because of the quirky nature of quantum mechanics, there's it's like rolling the dice. There's a randomness to it, right? But here's another cool stuff. Quantum superposition also introduced another concept called quantum interference. So what that means, all the inputs we work with start to interact in a very interesting way. Sometimes they cancel each other out. That's what we call the destructive interference. And sometimes they team up and try to enforce each other. And that's the constructive interference. And guess what? The interference magic turns out lead to the final result, predictable and deterministic. So although things start off a bit random, but in the end, it comes the way that makes perfect sense. So from random to deterministic. So that's the beauty of quantum interference. So starting in 1995, when Peter Shaw discovered Shor's quantum factorization algorithm, we have seen a massive increase in the number of research papers on quantum information and quantum computing published in top scientific journals. These immense growth mirrors the fascinating growth and rapid progress in the field of quantum information. So you can see the publishing numbers up to that's a little bit after 2010. It's already each year around that kind of amount. So after recognizing the significance of quantum information, the next key question is how to generate or how to make it a reality. So at the present, there are several qubit platforms which hold promise for realizing quantum information. My preferred choice is to work with single photons and neutral atoms. The motivation behind this choice stems from the unique and complementary properties between these two systems. So single photons with the minimal interaction with the environment, so offers the qubit, exceptional qubit stability, that making them ideal for long-distance quantum information transfer and networking. On the other hand, neutral atoms provide a solid foundation for qubit storage and manipulation, and boost the coherence time remarkably. So that's paved the way for robust quantum computing. So now when you combine these two elements, our goal is to harness the strengths of both systems aiming for scalable and efficient quantum information technologies that have the potential to revolutionize computing and networking and beyond. So here we would like to highlight a recent breakthrough. So coherently prepared neutral atom have just set a world record in quantum memory. So they have demonstrated remarkable ability to store quantum information carried by single qubits for extended periods, setting new standards in the search for dependable quantum memory solutions. So these accomplishments certainly paved the way for other quantum applications. So that's the achieved result. This is currently that's the record. So single photons, pretty much like the messengers of quantum states, they encode quantum information into their various degrees of freedom, like polarization, time energy, space momentum through their wave function or wave packets. So on the other side of the coin, we have neutral atoms that are carefully prepared using techniques like laser cooling trapping, optical pumping, or optical tweezers. These atoms create an excellent platform for interacting the quantum information carried by these single photons. With this setup, we can process various quantum operations, including single qubits and two-qubit gate operations, which are essential for quantum information processing and the dream of quantum computing. So now, if you put these two pieces together, it's like you have a dynamic duo that's propelling the advancement in quantum technology. And that's exciting, since it's going to change the way we do computing, networking, and communications.
Hey, Jianming.
Yes?
So where is the information stored?
Stored in the photons through polarizations, or time energy, or space-time. That's space momentum. That's the degrees of freedom. So later on we will show the picture.
What's the role of neutral atom?
Which one?
What's the role of neutral atom?
Neutral atom. So that's a usually alkali atom, like rubidium. So later on you will see that's like here, rubidium. Rubidium 85 or rubidium 87.
My question is very naive. Like, why a combination of photon and neutron?
Oh, photons. That's the fastest information carrier with the minimum interaction with the environment. So that means its coherence will be preserved, right? And the neutral atom turns out that's so far that's one of the best quantum interface that's allow you to coherently interact with the incoming photons. And since photons, that's our qubits. That's the one we're gonna send our quantum information. Okay. So then we use the neutral atom to perform the following gate operations and other kind of yes. So that's the way totally different from classical computer. So let's picture a picture of how a future quantum network can be make a reality using single photons and neutral atoms. So picture this: we send quantum information riding on single photons, like the one that's single photon, from one node to another. So even if these nodes are far apart, so using optical fibers or send simply through free space, and then at each node, single trapped neutral atom snuggled in a cavity or a group of atoms ready to work their quantum magic. So these atoms will coherently interact with the incoming photons, then processing the information in a way that we aim for. Okay. So now, if with additional help of Bell measurement at each node, then we are not simply talking about a quantum network, but also the possibility of the distributed quantum computing. So in other words, we are looking at the blueprint for an exciting future where quantum network and quantum computing could become the new norm. So currently we are trying to build up this type of quantum network. At least we try to demonstrate 5 nodes. So here's an artist's rendering of what a future quantum local area network or QLAN might look like. So although we have a preference for utilizing single photon and neutral atom for our quantum information endeavor, but it's important to know that there are other qubit systems making waves in the market today. So first up, we have trapped ions, a field pioneered by David Weiland, a Nobel Prize winner in physics back in 2012. So currently, Honeywell and IQ are the major players in this arena, with impressive demonstrations of 20 coupled trapped ions. Then we have superconducting circuits, where Google, IBM, Rigetti, and D-Wave lead the charge. So the number of coupled superconducting qubits varies depending on whether they choose two-dimensional or three-dimensional design. So with 50 for two-dimensional and only a few for three-dimensional. Moving on, we encounter silicon quantum dots with Intel and HRL as the key players. Although they managed to couple a few quantum dots together for simple quantum operations, it's an exciting field to watch. The first system to mention is topological qubits, where Microsoft stands as the sole player in this direction. But unfortunately, as of now, a single topological qubit has yet to be demonstrated even in a lab setting. There are more qubit systems out there, including those based on nitrogen vacancy centers in diamond and integrated photonic structures. Continue our exploration of quantum information, it's worth mentioning the Nobel Prize in Physics from last year. So this prestigious honor was awarded to Anna Isabel, John Clauser, and Anton Zeilinger for their groundbreaking work with entangled photons. So they not only established the violation of Bell inequality, they also laid the foundation for quantum information science. So Clauser deserves credit for proposing the first practical Bell inequality, and nowadays known as the CHSH inequality, which opened the door for experimental testing. He also conducted the first experiment of its kind with entangled photons emitted in atoms. Then Alan Asbeth made a significant contribution by explicitly demonstrating the violation of Bell, the CHSH inequality with improved entangled photon source, and resolving a major loophole in Clauser's experiment. And meanwhile, Zeilinger pioneered multi-photon entanglement and also made a very original contribution to various quantum information experiments, that's including the realization of quantum teleportation and entanglement symbology. So these, unfortunately, we won't touch in today's talk, like quantum teleportation. So at the start of our talk, we touched upon the idea of superposition involving more than one qubit. Actually, that leads us to the concept of quantum entanglement. So in the realm of quantum information and quantum computing, quantum entanglement is a fundamental factor. So to illustrate, let's look at a simple scenario with two qubits. And each qubit is represented by horizontal, single photons horizontal and vertical polarization. So now if we superpose two such polarization qubits, we will end up with two sets of maximally entangled Bell states. In other words, both qubits can either align along horizontal or vertical polarization, or one goes horizontal, another goes vertical, and vice versa. So these states are called maximally entangled because they allow for the maximum violation of Bell inequalities. So in other words, if you add any extra components to these two states, you will reduce their degree of entanglement. It's interesting to note quantum entanglement predicts the birth of quantum information. So back in 1935, Einstein with his colleague Podolsky and Rosen published a groundbreaking paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" So what's particularly intriguing today is this paper not only posed a question as its title, but also lacked any references. Think about it, nowadays if you publish a paper without any reference, you think the editor will allow you to publish? No way, right? And that's the one started, no any references. So in this influential work, we introduce a thought experiment involving a magical source which is capable of emitting two spatially correlated particles, say A and B. Since Einstein firmly rooted in the classical physics of the concept of local realism or locality, he argued that if you measure the position of one particle, then you can immediately predict the precise position of the second one. And similarly for the momentum. They contended that no action on one particle can instantaneously affect on the other, since that implies information transmission faster than speed of light, and violating the fundamental principles of relativity. Then they conclude, they call this action as a spooky action at a distance. Then they conclude quantum mechanics is incomplete, and there's a hidden variable interpretation to describe. And this is the famous EPR paradox. Since its publication, the EPR paradox has stirred immense interest in the scientific community, sparking lengthy and fruitful debate between Einstein and Niels Bohr and their followers. So these early discussions are often philosophical in nature, so leaving both sides unconvinced. So a significant turning point came in 1964 when, with the groundbreaking work by John Bell. So in that year, John Bell derived his famous Bell inequality, which starkly highlighted the disparity between classical physics and quantum mechanics. So his work inspired further research, leading to many Bell-like inequality, including the CHSH inequality for different entangled systems. So if based on the CHSH derivation, so Einstein's theory will lead to a quantity that's bounded by 2. Turns out quantum mechanics can go beyond this bound. So that showed the disparity. So over half a century efforts, we have made a significant strides in creating better two-photon sources and develop nearly perfect single photon detectors. And these efforts eventually allow us to have the perfect Bell test. So that means we're closing all the loopholes arising from non-perfect biphoton source, non-perfect single photon detectors, and also other issues. So among these other issues or loopholes, here we particularly wanted to point out 2. So one is related with the measurement basis, which ideally should be the measurement basis. So that's the picture like I showed here. Okay. So which ideally should be fully rendered to prevent any correlated results. Otherwise, the hidden variable interpretation that's favored by Einstein will find a room to sneak in. Okay. So this freedom of choice loophole was effectively addressed in an experiment involves thousands of observers for Bell measurement simultaneously a few years ago. That's led by the Boulder, UC Boulder group. Involves thousands, people simultaneously online in a few hours. And that paper published in Nature. Another loophole related with the spatial separation. That's related to the spatial separation. When you marry the entangled photons. So if the two photons here, if the two photons here are not far enough, then the result of one measurement will influence the other without violating the relativity. So to close this locality loophole, the experiment have to be conducted with long distances. So that the measurement on one party won't affect the other. This includes a recent, Bell test involving one photon detected on a satellite and its twin photon measured on Earth by Pan's group in China. And this paper published in Science a couple of years ago. So it's entangled particles are essential for Bell test and quantum information. Then the next key question is how to generate such entangled particles. So in early days, people tried to derive paired photons from the two photon emission process in atoms, like Colloquium and SFWM work. But unfortunately, that method had low generation efficiency, and also the generated paired photons are less entangled. So a breakthrough came with the use of nonlinear optical processes operating at the spontaneous emission region. And my PhD group pioneered the well-known SPDC source in the early 1980s. So by pumping a nonlinear crystal with the second order nonlinearity with a CW pump laser, then we can down-convert a pump photon into two correlated new photons called signal and idler, following the energy and momentum conservation, or the so-called phase matching conditions. And later on, people found that spontaneous Fourier emission in a third-order nonlinear optical medium could also produce high-quality entangled photon pairs. So in this process, absorbing two pump photons lead to the emission of two new correlated photons called Stokes and anti-Stokes along their phase matching directions. So nowadays, these two types of biphoton source have become the main driving force in research and technological development. To ease the following discussion, so let's get a clear picture of the traditional SPDC biphoton source. So historically, there are two types of SPDC processes, depending on the polarization of the generated Stokes and anti-Stokes photons. So in type 1, both photons share the same polarization and emitted from two cones. So this real photo that's taken by my PhD group in 1994 clearly shows the broad bandwidth and multi-wavelength characteristics of spontaneous type 1 SPDC photon. So different from type 1, in type 2 SPDC, it can naturally produce orthogonal polarizations. So that means this allows us to easily generate polarization Bell states we mentioned earlier from these intersection areas. And again here, you can see the broad bands and multi-wavelength features appear in type 2 SPDC too. So although SPDC can efficiently generate high-quality entangled photon pairs, their bandwidths are too broad, typically in the terahertz range. And their coherence time turns out too short, only a few picoseconds. And their coherence length is also very short, only a few millimeters. So that makes them not good for interacting with various quantum interfaces like neutral atoms. So that drives us to look for a narrowband biphoton source. So before jumping into our contribution, let's understand how a signal and idler are correlated in SPDC process. So since this correlation that underpins various quantum applications. So in experiment, we use a technique that's called two-photon coincidence counting. That's originally from high-energy physics to study their correlations. And in theory, we rely on Glauber's quantum coherence and the photon detection theory. So after some calculations, we can show the SPDC photons can be completely described by this pure wave function. So which is a coherent superposition of many two-photon states. So in this wave function, there are two Dirac delta functions. So one for energy conservation. So that means if one photon trigger one detector, its twin photon must trigger the other single photon detector at a well-defined coincidence time window. And that time, this coincidence window is defined by this wave number mismatch function that's related with the photon dispersion. And another delta function relates to the momentum conservation. It states if one photon detected at one specific location, then its correlated photon must be detected at well-defined position. And this temporal and spatial correlation turns out that set the basis for quantum application in imaging, lithography, metrology, sensing, radar, and even clock synchronization. Their performance well beyond the classical means. So we realize, that wave function. So here we plot it for type 1 and type 2 SPDC photons. So this wave number mismatch function defines the correlation time between the class of the two single photon detectors. So in type 1 SPDC, both signal and idler experience the same dispersion. So that's creating the symmetric profile around origin in this T1 and minus T2 axis. However, in type 2 SPDC, one photon will travel faster than the other. So that leads to nearly square profile away from the origin. So after understanding, how SPDC biphoton generated, now let's look at our contribution. To create a narrowband biphoton, we have pioneered a new method using coherent atom that's in a magneto-optical trap or glass cell to directly generate narrowband biphotons near atomic resonance through the spontaneous four-way mixing. So these methods stand out from other approaches, including using high quality cavities. So in this approach, we input two CW lasers called probe and control to enable the generation of paired stones and anti-stones along their phase matching directions. So besides the flexible detection geometry here, these generated photons have all the necessary qualities for quantum information technologies based on single photons and neutral atoms. So their bandwidth is pretty narrow, usually around the range of megahertz. And their temporal coherence time is pretty long, ranges from tens of nanoseconds up to milliseconds. And most importantly, we can fully control the two-photon waveform simply by tailoring the atomic properties in time. And that's impossible or challenging for any solid materials. And since its initial demonstration, this new source has garnered increasing interest within the scientific community. So to understand how stones and anti-stones are related here, let's take a quick look at their temporal wave function. As you can see here, there's a significant difference from SPDC case. And this third order nonlinearity term appears and becomes a new knob to shape the two-photon waveform. So if this third order nonlinearity dominates over the wave number mismatch function, then the two photon correlation leans towards this nonlinearity, unlike the SPDC case. If this wave number base function is dominant, then it steers the two photon correlation more towards SPDC. And experiments here indeed confirm this interplay. So with low atomic density, the biphoton generation shows damped Rabi oscillations, where this third order nonlinearity turns out to play the essential role. At high atomic density, biphoton generation was pushed into the opposite region. That's what we call the group delay. And in this region, the wave number mismatch function is essential. And more interesting in this latter region, the sharp peak always appear near the 0 time delay between the case of the two single photon detectors. This is because a fraction of paired photons doesn't experience any dispersion and always propagate at the speed of light in vacuum. And this phenomenon, known as the optical precursor effect, was proposed by Brilliant and Sommerfeld over a century ago, but now it's observed at the two photon level. And importantly, this effect is unique to our source and cannot be observed with SPDC and any other solid biphoton materials. So in the previous experiment, we used 4 and 3 level code atoms to generate narrowband biphoton. In 2007, we also experimented narrowband biphoton generation in a two-level code atomic system, only using one retroreflected pump beam. So interestingly, this work recently was replicated by Chandra Raman's group at Georgia Tech. They use, a warm atomic vapor. So our result displayed here, which is certainly different from the previous patterns, in that the two photon coincidence constant here shows symmetric around the origin. So this is because destructive interference occurs between two types of spontaneous four-way mixing processes that's involved in biphoton generation. And these two processes are indistinguishable to the current commercial single photon detectors. So in one process, both photons share the same central frequency as your input, pump laser. And in the other process, their central frequencies are shifted oppositely by an effective Rabi frequency. So now if we plot these biphoton spectra together, turns out they form the well-known mono triplet, except here observed at the two photon level. So with our narrowband biphoton source, we have demonstrated their crucial roles in quantum information applications based on single photons and neutral atom. So that includes, our demonstration of optimal single photon storage and retrieval for quantum memory. But unfortunately, due to time constraint, we won't touch those topics in today's talk. So here we would like to highlight our recent breakthrough in generating the first reliable, genuine W-class triphoton source. So before our work, triphoton and multi-photon entangled states were reported using post-selected biphoton sources, but all those non-reliable, not all those non-reliable. So, and the W-class tripartite entanglement is so unique. So if you lose one photon in this triphoton pair, then the remaining two still maintain non-maximal entanglement. And this makes make this triphoton pair robust to photon loss. And that's essential for many quantum information and computing protocols. So in this experiment, we directly generate narrowband triphotons through the process of spontaneous cis-wave mixing in a hot rubidium vapor cell. So we input 3 classical CW lasers, E1, E2, and E3, to generate 3 simultaneous newborn photons. That's ES1, ES2, and ES3, and detected them by 3 single photon detectors. So using a homemade 3-photon coincidence circuits, we then can study triphoton correlation. So here why we have to use homemade, since there is no any multi-photon coincidence circuits in the market. If you purchase, you can only get a coincidence, 2-photon coincidence circuit. Go beyond 2, you have to make it by yourself. So much like our narrowband biphoton generation. So the triphoton temporal correlation here also depends on the interplay between the nonlinearity. So here the nonlinearity belongs to the 5th order nonlinearity, and also the wave number mismatch function. So in one experiment, we use the low atomic density, so generate the triphoton, and the experimental result that is shown here. So which shows that the Diamond-Rabi oscillations when we measuring the ES1 and ES2 photons, or when we measuring the ES1 and ES3 photons. So this clearly demonstrates the W-class signature that we mentioned before. Okay? And in this experiment, the triphoton production rate is reached approximately 6,000 pairs per hour. That's already a record. If we in another separate experiment, so we tweak the system parameters to modify the triphoton temporal correlation. For example, if we change the power and the frequency detuning of the second pump laser, then we can see the appreciable change in both 3-photon and conditional 2-photon correlation patterns. And in another experiment, we push the atomic density too high, so that we make sure that the 3-photon generation can reach the group delay region. And in these, if you compare with the other two, so now you can see the temporal coherence time and the production rate certainly get largely improved. So before we wrap up, let's take a quick look at the latest development in quantum hardware for popular qubit system. So as you can see from this graph, so neutral atom certainly excels in scalability, boosting significantly a higher number of atoms here. On the other hand, trapped ions lead the pack in terms of qubit control and configurability. And the superconductor turns out it's in the middle. Currently in the US market, trapped ions and superconducting circuits are the leading candidate for quantum computer hardware. So these slides summarize their major features and major challenges. So you can see why these so good. Certainly, there's a lot of stuff you need to overcome. The too low temperature, right? That's certainly a big issue for superconducting circuits. So that's why we wanted to look at the other direction. And by the way, so early of this year, especially Germany, they launched a big program, put $30 billion to develop a quantum computer simply based on single photons and neutral atom. They don't believe no matter trapped ion and superconducting circuit eventually will win the game. Another point we want to address is regarding the D-wave. So far, D-wave hasn't truly demonstrated quantum supremacy in computing. And more importantly, their machine doesn't involve any quantum base at all. So that's we put the question mark. Is it really quantum? Okay? So no doubt if you purchase this machine from Canada, that's at least a few $1 million machine. With that, then pretty much we will reach the end of this talk. So here we provide a concise overview of quantum information by highlighting single photons and neutral atoms, and especially entanglement generation. So with that, then I'm ready to take your question. By the way, so both my wife and me, we have, no matter postdoc position or under research, positions. So we welcome you to join. And both me and my wife have, a quantum optics lab. So here in the SFWM College, that's supported by IBM. So I also have, a quantum optics lab at the GSU. So if you really want to see whether really, a single photon or what it means correlation, then you are welcome, to stop by. Definitely we can demonstrate that for you.
Curious, you've used rubidium in your vapor cells, but what about the other alkaline metals like potassium, sodium, cesium?
Yeah, cesium, that's another good one. Yes, but I prefer rubidium.
Why?
Why? The wavelength. Since the wavelength there is near the visible range, and that's the best part, for single photon detector. So you have a nearly unit detection efficiency. Yes. But when you use a system, then that's already away from the visible, right? And that part, the detection efficiency dropped quite much. So here, that's why we mention single photon. That means we target it as a visible light. Now we don't care about superconducting that kind of light. That's a microwave, right? So that part certainly cannot do any kind of free-space transmission. Okay, and also for superconducting, as we just said, depending on the two-dimensional and three-dimensional design. A two-dimensional design that's like a Google, like UCSB lead in this kind of direction. For that kind of design, it's hard to engineer or manipulate each single qubit. And that's not good for any quantum information processing or quantum computing. And the three-dimensional then allow you to tune each qubit. But unfortunately, its scalability become the biggest solution. So that's only a few superconducting qubits currently can realize and cover. Yes?
Yeah, toward the end of the talk, you mentioned the convergence. Yeah, that is,
Which one?
yeah, there's a class with the number of particles and also
Oh, the one here.
Yeah, very end. Here, yes. Yeah, so that's exactly the thing I was thinking about. So, so in your system, any ideas how to practically use it in your own computation?
What? Can you repeat?
Yeah, so any ideas for how to use it for computation? I mean, you can demonstrate the entanglement, but
Yes, that's not enough. So far, IBM can only have 5 to 6 superconducting qubits, and the first qubit have very good performance. So all the parameters are super good, but the second one immediately then drop a little bit, and the third one then drop further. And when you reuse 5 qubits together, try to do really something. That certainly can do something. But turns out, it cannot show the power that can overperform any kind of classical computer. Since in order to show quantum supremacy for qubits, at least there should be over 100 coupled qubits together. And so far, we haven't reached that. So that's why we wanted to, separate the whole goal into these small pieces. The first part, we wanted to realize the distributed quantum network. And then later on, then based on each nodes, we can have perfect performance, no matter in information processing and a small beta operation, or that's a so-called small part of quantum computation. Then later on, through the networking, then you can realize a quantum computer. So that's the new solution called distributed quantum computer. So right now, we believe the most promising way to realize quantum computer, not just a standard use. You realize a quantum computer in one lab. That's not the way you can do it. So probably we need to use like optics or optical fiber or even for space, need different labs together, and then eventually we can they work together and then form a quantum group. Yeah. So for the right now, there's no way to demonstrate real quantum computing power yet. No any real demonstration.
Because I work on nuclear physics, and there are a lot of evidence that nuclear system is highly entangled.
Yeah, the problem, entanglement is everywhere. Why we say that? Entanglement, remember, based on the superposition. And the entanglement, another way, if through this talk, except I didn't mention clearly, if there's an interaction, there is a high chance of possibility to get entanglement. The issue is that how you gonna isolate your entanglement, how you gonna manipulate your entanglement, how you gonna preserve your entanglement. That's the issue. So that's why even no matter like biology, chemistry want to jump in this field, yes, certainly we welcome, but we don't believe if only with their work they eventually compute up quantum computer. So quantum computing is somehow kind of two picture. Yeah. Yes.
Yeah, I have questions which are closely related. If one works with two particles which are entangled, can one somehow bypass Heisenberg uncertainty principle because one
No.
can, okay.
That's the one I can bring you. So that's related with the quantum sensing. So Heisenberg limit is the fundamental limit. Okay. So no matter how much entanglement you have, like a multi-partite entanglement, you can the limit always gonna bounded by the Heisenberg that limit. In other words, you reach the minimum, and you cannot go beyond that minimum. It's always bounded by that. So theoretically, we can prove.
And for causality, right?
Causality never violated. So here I didn't mention too much for this Bell tests, and that's involved too many kind of philosophical arguments. So but here we can see something. Since remember the two photon or the entangled states is a pure state, right? So any pure state, if you but shared by the two particles. If you only look at one, then its state is a mixture state. In other words, there is no complete information. So like the light bulb, if you only look at one, turns out you can never precisely predict whether it's on or off. It's always going to be a statistical mixture. So in other words, the Einstein argue, that's going to violate causality. Actually, that's not really an issue at all. So here, why this Bell test is so famous? Not only due to this spooky action at this, it's due to other kind of loopholes like here. So I didn't say too much, like a free will. So free will is also another kind of philosophical argument. So said any kind of measurement device has intelligence. They can choose whatever they want to do, not the way you design want them to do. So that's the one I said, the measurement, the freedom choice for the measurement basis. Okay? So if only one, hold on a second, sorry. So if only one do the experiment, then you cannot preclude, this kind of bias. So that's why Boulder's experiment involves thousands, anomalous, people online just said, hey, that's our measurement, result. You just choose whatever kind of basis you want to formulate, okay? And then they try to generate, your picture, like the picture. So like the picture shown here. So you can generate, your own picture, and they see whether your picture violates, Bell inequality or not. Yes.
Yeah. So I think he asked the question I wanted to ask. So, but I will connect it to something. See, maybe I'm thinking after his question. I was thinking about the same thing, but
Yes.
you mentioned A and B, two particles.
Yes.
And you said that once you know all the properties about A,
Mhm.
they are interacting particles, you know everything about B. See, I know.
That's not fully exact. That's I repeat. That's I quote. That's EPR paper.
Okay, so
Okay.
what,
So here another story behind. Actually, involves the Fourier, optics. If you can predict, the position, you have a perfect position. The momentum you cannot have it. That's the issue for EPR argument. That's one, big mistake they make. So if you consider, the Fourier transform, certainly many of you will know Fourier transform, right? So optics can do that. So if you use, 1 degree of freedom, like you working on time, then you doing Fourier transform can look at the frequency, right? So if time is perfect. Turns out the frequency here gonna be infinity. There's no way you can make any kind of a prediction. So that's why here the logic already make a mistake. Unfortunately, at that moment, even after so many years, Einstein didn't realize that.
One simple, another technical question. You mentioned silicon quantum dots, I think HRL labs or somebody is making them.
Yeah.
So my question is, how do they make the silicon quantum dot? Which way? Do you know?
I don't know. So the part, for this silicon quantum dots, to me, I'm not a fan of it.
So the reason I'm asking this is, if it is self-assembled, you cannot control the size of the dot.
Exactly. That's why it
You cannot control the size of the dot. How are you going to get some property the way you want?
Yeah, there's a way. There's quantum objects already developed. So many tools allow us to make sure the photon emitted from one quantum dot and another from another quantum dot. It are definitely totally indistinguishable. That's a so-called fundamental deep interference. Okay, interference, obvious. So when involved, no matter in quantum information, quantum computing, you can never get rid of quantum interference. So that's why at the beginning I made that the slides. Yes.
With your current system, with the entangled photons and neutral atom system that you have, with respect to actually going from an entangled system to actual quantum computing, how are logic gates done? Quantum logic gates done in your model, in your system?
The logical qubit. First of all, let's get the qubit. Qubit always the fundamental. So here, the one we said, in place state. Thank you for that, important question. So for qubit, you should really be careful. So qubit here, okay, covers, both a physical qubit and a logical qubit. And logical qubit usually formed by more than 2 qubits, physical qubits. Okay, so the one here, in order to have a logical qubit, that means we need to send a bunch of single photons, and each photon behave as one physical qubit, and then we can encode the quantum information there through like a polarization, right? Vertical and horizontal. Yes, and then later on you can process, and that is the one actually logical qubit has already been done in that iteration. I didn't put it here. So however, when you couple, I want to have 2 coupled logical qubit, that's extremely challenging, even at this moment. So the one we said couple, the qubit together, that means we couple physical qubit, not logical qubit yet. Yeah.
Sure. Other questions? If not, let's the next document brief.
Thank you. Sorry, too much jargon, right?